Alright, hello students. This is the little video that comes with the lesson online. So I'll play that as a video in so that you can put this in with lesson 17. So all you have to do is just listen and watch.
Of equations. Welcome to video 5 for this unit on linear equations, inequalities, and systems. In this video, we're going to focus on solving systems of equations. The solution to a system can usually be found by graphing, but graphing may not always be the most precise or the most efficient way to solve a system. Here is a system of equations. The graphs of the equations show an intersection at approximately 20 for P and approximately 10 for Q. Without technology, it is not easy to tell what the exact values are. Instead of solving by graphing, we can solve the system algebraically. Here's one way. If we subtract 3p from each side of the first equation, 3p plus q equals 71, we get an equivalent equation. Q equals 71 minus 3p. Rewriting the original equation this way allows us to isolate the variable q. Now we can substitute the expression 71 minus 3p in the place of q in the second equation. Doing this gives us an equation with only one variable, 2p, minus the quantity 71 minus 3p equals 30, and makes it possible to find p. Now that we know the value of p, we can find the value of q by substituting 20.2 for p in one of the original equations and solving. The solution to the system is the pair p equals 20.2 and q equals 10.4, or the point 20.2, 10.4 on the graph. This method of solving a system of equations is called solving by substitution, because we substituted an expression for q into the second equation. Another way to solve systems of equations algebraically is by elimination. Just like in substitution, the idea is to eliminate one variable so that we can solve for the other. This is done by adding or subtracting equations in the system. Let's look at an example. Notice that one equation has 7y and the other has negative 7y. If we add the second equation to the first, the 7y and negative 7y add up to 0, which eliminates the y variable, allowing us to solve for x. Now that we know x, we can substitute 10 for x in either of the equations and find y. The solution to the system is x equals 10 and y equals 2. When solving a system with two equations, why is it acceptable to add the two equations, or to subtract one equation from the other? Remember that an equation is a statement that says two things are equal. For example, the equation a equals b says a number a has the same value as another number b. The equation 10 plus 2 equals 12 says that 10 plus 2 has the same value as 12. If a equals b and 10 plus 2 equals 12 are true statements, then adding 10 plus 2 to a and adding 12 to b means adding the same amount to each side of a equals b. The result, a plus 10 plus 2 equals b plus 12, is also a true statement. As long as we add an equal amount to each side of a true equation, the two sides of the resulting equation will remain equal. In other systems, which strategy to use is less straightforward, either because no variables are isolated or because no variables have equal or opposite coefficients. For example, 2x plus 3y equals 15, and 3x minus minus 9y equals 18. To solve this system by elimination, we first need to rewrite one or both equations so that one variable can be eliminated. To do that, we can multiply both sides of an equation by the same factor. Remember that doing this creates an equivalent equation, so the x and y values that make the first equation true also make the new equation true. There are different ways to eliminate a variable with this approach. Let's try this. Multiply the first equation by 3 to get 6x plus 9y equals 45. Adding this equation to the second equation eliminates y. Substituting 7 for x in the second equation allows us to solve for y. The solution to this system of equations is x equals 7 and y equals 1/3. We've seen several examples of a system where one pair of values satisfies both equations, but some systems have many solutions and others have no solutions. Let's look at 3 systems of equations and their graphs. The graphs of the equations in this system intersect at one point. The coordinates of the point are the one pair of values that are simultaneously true for both equations. When we solve the equations, we get exactly one solution. The graphs of the equations in this system appear to be the same line. This suggests that every point on the line is a solution to both equations, or that the system has infinitely many solutions. How can we tell without graphing that this system indeed has many solutions? Notice that 3x plus 4y equals 8 and 6x plus 8y equals 16 are equivalent equations. Multiplying the first equation by 2 gives the second equation. This means that any solution to the first equation is a solution to the second. The graphs of the equations in this system appear to be parallel. If the lines never intersect, then there is no common point that is a solution to both equations, and the system has no solutions. How can we tell without graphing that this system has no solutions? Notice that in one equation, 3x plus 4y equals 8, but in the other equation, 3x plus 4y equals -4, because it is impossible for the same expression to equal 8 and -4. There must not be a pair of x and y values that are simultaneously true for both equations. This tells us the system has no solutions. Thank you for watching video 5 of 7 for this unit on linear equations, inequalities, and systems.